Drawing Lewis structures, part 1. Bum, bum, bum. In this part, we're going to introduce you to the basic concept of Lewis structures and tell you how to draw Lewis structures for some very simple molecules. In part 2, we'll kick it up and deal with some formal charges and some more complicated scenarios. But let's get right off to the start, a quick start, by talking about what we're talking about. Well, there was a well-duh statement if I ever heard one. A Lewis structure is a way of visually displaying the two-dimensional connectivity of a molecule. A Lewis structure is in a Lewis structure, a straight line is used to represent a pair of electrons, usually in the context of a covalent bond. A lone pair of electrons can be represented by two dots. A single dot represents a single electron. You'll also see me use X's to represent single electrons. The different elements and atoms themselves are represented using their elemental symbols. A lot of the functionality of a molecule stems from its three-dimensional shape, and its three-dimensional shape stems from its two-dimensional connectivity. So there's big money and big importance placed on understanding this two-dimensional connectivity. And Lewis structures is one of the ways we display this information. In order to understand how we're going to construct Lewis structures, it helps to quickly remind ourselves of the Octet Rule. Remember, the Octet Rule is the desire of elements to have a completely filled outermost S and P subshells. And remember, since the S holds 2 and the P holds 6, for most elements, that means they want 8 electrons in their valence shell. Hence, the Octet Rule. How different elements obey this Octet Rule is going to differ. That, too, bears reminding. We're going to look at the different groups on the periodic chart real quickly. It turns out that elements in group 4A attempt to achieve the Octet Rule by forming 4 bonds. Elements in group 5A attempt to achieve the Octet Rule by forming 3 bonds. And guess how many bonds group 6A is going to form? 2 bonds. And elements in group 7A are going to achieve the Octet Rule by forming 1 bond. How about elements in group 8A? They already have 8 valence electrons because there are noble gases, and they're not going to do anything. But that's just a quick reminder. And you're saying, Dr. Kelly, what about the metals? Well, we already talked about ionic compounds. In the context of what we're doing currently with our simple Lewis structures, we're not going to worry about metals. We're not going to be dealing with any coordination compounds quite yet here. But it's very important that you keep this preferred bonding in mind. How is this important? Well, if we look at our example I drew on the other side there, where I drew the Lewis structure of water, I never actually acknowledged its existence on the last slide, but I drew it for you. If you look at this Lewis structure of water, oxygen is in group 6A, right? And how many covalent bonds does it have? It winds up forming 2. If I was to look at, let's say, natural gas, methane, look how many bonds carbon has. 1, 2, 3, 4. What group is carbon in? Carbon's in group 4A. Knowing how many bonds an element wants to participate in will help us draw our Lewis structures and save us some work later on. So those are things to keep in your back of your mind as you move forward. Also moving forward, it would be a great idea if you wrote down Jolly Ranchers. Why don't you write down Jolly Ranchers? Everybody write down Jolly Ranchers. All right. How can we draw Lewis structures in just 4 simple steps, or your money back guaranteed? What, you didn't pay anything for this lecture? Why not? If I give you my mailing address, will you write me a check? Oh, wait, I'm sorry, that's old-fashioned. If I put a link down below, will you donate something to a PayPal account? Or wait, no, better yet, maybe I should use GoFundMe. Tell you what, how about we do Lewis structures now, and I'll figure out a way for you guys to give me money later. But at any rate, step 1. The total number of valence electrons. So if we're wanting to draw the Lewis structure for something, let's take a look at a very simple molecule for starters. Carbon tetrachloride. The first thing to do is total the number of valence electrons. I have carbon, and carbon's in group 4A if you look at your periodic table. And that means it has 4 valence electrons. We have 4 atoms of chlorine, and chlorine's in group 7A. So each one of those chlorine atoms brings 7 valence electrons to the table. 4 times 7 is 28. That gives us a total of 32 valence electrons. We have to find a home in our molecule for all 32 of those valence electrons. Not only that, but we can't exceed 32 valence electrons in our structure. I like to think of this total number of valence electrons as my building fund. That's how much money I have to spend to build my Lewis structure. So that's step 1. Established our building fund. Our next thing to do is to draw our skeletal structure. What do I mean by our skeletal structure? What we want to do now is we want to determine A, who our central atom is going to be, and then B, how those things connect to it. Most of the structures we're going to start looking at with Lewis structures are all going to have a format where you have one central atom and a bunch of other things connected to it. The hard part is figuring out who that central atom is. There's a couple easy ways to do this. First, carbon loves to be the central atom. Carbon actually has the elemental symbol C, not because carbon begins with C, but because C is for central. C is for central, which is good enough for me. All right, so C is for central. So carbon's going to be our central atom. I'm then going to connect all the other atoms in my structure to that central atom. So I have 4 atoms of chlorine that I want to connect to my carbon. So I drew 4 lines between I connected my chlorines to my carbons by drawing 4 lines. Now, these lines represent a covalent bond, which, as you know, is a shared pair of electrons. And how many is a pair? 2. So how many electrons did I use to draw my skeletal structure? I used 2, 4, 6, 8 electrons to build that skeletal structure right there. So I have to come over here to my building fund and subtract 8 electrons. So I've used 8 electrons to build my skeletal structure. That means I have 24 electrons left to complete my Lewis structure. For step 3, we want to complete the octet of the non-central atoms. At the moment, each one of our chlorine atoms has 2 electrons. Each one of our chlorine atoms is participating in one bond. So if I focus just on this chlorine atom here, it has 2 electrons from the bond. To complete its octet, how many more electrons does chlorine need? Chlorine needs 6 more electrons to have a total of 8, since it already has 2 from that bond. So if I'm to give this chlorine 6 electrons, 1, 2, 3, 4, 5, 6, it now has 8. Each one of these chlorines only has 1 bond, so each one will need 6 more electrons to complete its octet. Now I have 4 chlorines, and I gave each one of those chlorines 6 electrons. That means I used a total of 24 electrons. So I have to subtract those 24 electrons from my building fund. Oh no, that exhausts my building fund. So I'm out of electrons. That means it's time for my last step. I'm going to check and see, is everybody happy? Alright, I'm out of electrons in my building fund, so I need to check and see, is everybody happy? And by happy I mean, do they all have a complete octet? So my chlorine has 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Are you asleep yet by me saying 2, 6, 4, 8, 2, 6? So all my chlorines are happy, right? They all have 8 electrons. How about carbon? Let's count for carbon. Carbon has 2 electrons from this bond, 2 electrons from this bond, 2 electrons from that bond, 2 electrons from that bond. So carbon has 2, 4, 6, 8 electrons as well. So it has a complete octet, so it's happy. So everybody got what they wanted by participating in this molecule. That means we're done. And that's our Lewis structure for our carbon tetrachloride. Now some of you are saying, wait a second, Dr. Kelly. Are you trying to wrap me up in some sort of weird pyramid scheme? What sort of racket are you chemists pulling here? After all, I distinctly remember you looking at this chlorine right here and counting 2, 4, 6, 8 and saying that these electrons right here were 2 electrons belonging to chlorine. And you're right, I did say that. But then you're saying, wait a second, Dr. Kelly. When you were counting for the carbon, you went 2, 4, 6, 8, and you counted these 2 electrons as belonging to carbon. But you had just counted those 2 electrons as belonging to chlorine. You're absolutely right. We double counted those 2 electrons, and that's allowed. Matter of fact, that's the reason these covalent compounds form. The electrons in our covalent bond here count as 2 electrons for our carbon and 2 electrons for our chlorine. We're in essence double counting them because they're a shared pair of electrons. It was this type of accounting that got us to mortgage-backed securities. But at any rate, yes, when it comes time to count the electrons belonging to each atom, we do double count those electrons in the covalent bond. Let's look at another Lewis structure. Alright, let's take a look at phosphorus tribromide. Anybody else hungry around here? This always makes me want a peanut butter and jelly sandwich. But at any rate, if I ever get to discover an element, I'm giving it the elemental symbol J, and I don't care what IPAC says, just so that I can have PB&J sandwiches on my periodic table. I'm just saying. And PJs, how cool would that be? But at any rate, I digress. We want to draw the Lewis structure for this compound. So the first thing we're going to do is we're going to establish our building fund. I have 1 phosphorus. Phosphorus is in group 5A on my periodic table. So it has 5 valence electrons. I have 3 bromines, and bromine, just like chlorine, is in group 7A. So it has 7 valence electrons, so 3 times 7 is 21, plus 5 is 26. So I have 26 electrons with which to build my molecule. The next thing I'm going to do is draw my skeletal structure. However, to draw my skeletal destruction, I have to know who the central atom is. I don't have carbon, so that makes my decision a little bit harder. Now, the formal rule says that I'm going to place the least electronegative atom at the center of my molecule. In this case, phosphorus is my least electronegative atom. Remember, electronegativity increases in the direction of those arrows. When in doubt, left and right takes precedence. But that's a pinky way out of determining it. A cheat way that I like to use, I call the bar rule. If there is one girl in a bar and 3 guys in the bar, what's going to happen? All 3 guys are going to crowd around and pay attention to the female in the bar. Correct? What happens if there's 1 guy in a bar and 3 girls? The 3 girls ignore him because they wonder why the loser's there alone. But at any rate, we have 1 girl in the bar and we have 3 guys. So they're all going to crowd around and pay attention to her. So we have just 1 phosphorus and 3 bromines. So all our bromines are going to crowd around and pay attention to our phosphorus. So in drawing our Lewis structure, phosphorus is not only the least electronegative, but it's the only girl in the bar. So all my bromines are going to bond with my phosphorus. And before you ask, it doesn't matter how you connect these. And what I mean by that is it would have been just as correct for you to have done that, or for you to have done that, or any other way you can turn it. All that matters is that you have your 3 bromines attached to your phosphorus via a covalent bond. I will mention one thing I was negligent in mentioning earlier. When we write Lewis structures, what we like to pretend is we like to pretend that each side of our elemental symbols is an orbital. We're trying to complete an octet, and you have 1 orbital in the S and 3 orbitals in the P. So if we were to look around our phosphorus, we would say that we have 1, 2, 3, 4 orbitals in our valence shell. So we like to pretend that we have 4 orbitals around our atoms when we draw them. In case you were wondering how that convention came about. Whoa, I just hit the wrong button there apparently because my skeletal structure just disappeared on me. But that's not a problem. Okay. So we draw our skeletal structure. How many electrons did it cost us to draw that skeletal structure? 2 electrons here, 2 electrons here, and 2 electrons here. So that's 2, 4, 6. So drawing our skeletal structure cost us 6 electrons. That leaves us with 20 electrons remaining. So now we're onwards to step 3. Complete the octet of the non-central atoms. Place any remaining electrons on the central atom. So I'm looking at bromine, and bromine has 2 electrons currently from the covalent bond. So to get an octet, or 8, it needs 6 more electrons. So I'm going to give it 6 more electrons. 1, 2, 3, 4, 5, 6. Now each one of these bromines is in the same situation. They each need 6 more electrons to complete their octet. And I have 3 bromines. So 6 electrons to each of my bromines times 3 bromines means that to complete my skeletal structure, I just used 18 electrons. 2, 4, 6, 8, 10, 12, 13, 14, 16. Yay, Dr. Kelly can count by 2s. So I used 18 electrons for my building fund. That leaves me with 2 valence electrons. I have to use all my electrons. This isn't private industry where I'd get rewarded for saving valence electrons. I have to use them all. According to my rule, I place any remaining electrons on the central atom. So I have 2 valence electrons left over, so I'm going to place those 2 electrons on my phosphorus. That leaves me with 0 electrons. So now rule 4, check and see, is everybody happy? Alright, so let's count and see if everybody has an octet. Our bromine has 2, 4, 6, 8. So that bromine's happy. 2, 4, 6, 8. So that bromine's happy. 2, 4, 6, 8. So that bromine's happy. And then our phosphorus, 2, 4, 6, 8 electrons. So our phosphorus is happy. So we're done. And just for kicks and giggles, our clean Lewis structure would look like, because I've written all over this one, so our clean Lewis structure would look like that. But you know what I always say? One good example deserves another. Let's do another example just to make sure we're all on the same page here. And let's take a look at water. I mean, we can't really get much simpler than water. Matter of fact, why don't you try pausing me and doing water on your own? All right, I hope everybody's had a nice drink and is coming back to me with a complete Lewis structure on their paper. Start by counting up your total number of valence electrons. We have 1 oxygen. Oxygen is in group 6A. We have 2 hydrogens. Hydrogen's in group 1A, so it has 1 valence electrons. 2 hydrogens times 1 valence electron each gives me 2 valence electrons from my hydrogen for a total of 8 valence electrons. Draw my skeletal structure. Well, 1 girl, 2 guys. So oxygen is going to be my central atom. And notice how that actually plays into my rule there. Remember, hydrogen can never be your central atom. That's another way we could have gotten the fact that oxygen was going to be. So oxygen's my central atom. To draw that Lewis structure, it cost me 4 electrons, because I had to draw 2 bonds at 2 electrons each. So I used 4 electrons to draw my skeletal structure. Now I want to complete the octet on my outlying atoms. Right now, hydrogen has 2 electrons, and it turns out that makes hydrogen happy. Remember, hydrogen is in the first period. That means its valence shell is your first energy level. And the first energy level only has the 1s subshell. And the s subshell can only hold 2 electrons. So hydrogen's valence shell can only hold 2 electrons, which means a long way short. Hydrogen can only handle 2 electrons. No more! Can't take any more than 2. All right. So we've taken care of that. Now we've still not done yet, because we have leftover electrons. Our hydrogens are happy. We've made our hydrogens happy here. So now we're going to place our remaining electrons on our oxygen, and we have 4 remaining electrons. So we're going to place all 4 around our oxygen. Now we check and see, is everybody happy? Well, our hydrogens are happy with 2 each, and our oxygen, 2, 4, 6, 8. So our oxygen is happy, and we're good. Chemistry's easy, life is hard. All right, let's take a look at this compound. We have carbon in group 4A, so it's 4 valence electrons. We have 2 hydrogens, and hydrogens in group 1A, so each has 1 valence electron, and we've got 2 of them for a total of 2. We have 1 oxygen in group 6A, So it has 6 valence electrons. So we have a total of 12 valence electrons to build our Lewis structure here with. Carbon's present, so it's going to be our central atom. So I'm going to connect my other 3 things to carbon. That means I have to draw 3 bonds and used up 6 of my valence electrons. Now we want to make our outlying atoms happy. Each hydrogen's happy because they already have 2 electrons. My oxygen, however, is not happy. My oxygen only has 2 electrons. It wants 8, so it needs 6 more electrons. 2, 4, 6. And now it has 8, but that used up the rest of my building fund. Now I have to check and see, is everybody happy? Well, oxygen has 2, 4, 6, 8. Each hydrogen has 2, and my carbon has 2, 4, 6. Uh-oh. What am I going to do? After all, I'm out of building funds. I don't work for the government. I can't just get more money out of thin air. Well, actually, I do work for the government. But anyway, I just can't get more electrons out of thin air. So how in the world am I going to complete the octet for this carbon? More creative accounting. Remember, an electron pair in a bond counts as 2 electrons for each atom. So to complete the octet for carbon, I'm going to move one of the lone pairs from around the oxygen so that it's between the oxygen and the carbon. When I do that, how does that change my electron count? Well, I now have 2, 4, 6, 8 electrons around carbon. How about my oxygen? My oxygen still has 2, 4, 6, 8. So everybody's happy. It's a win-win scenario. Know what is also a win-win scenario? A Reese's peanut butter cup. If you want chocolate, you get chocolate. If you want peanut butter, you get peanut butter. So why don't you write down Reese's peanut butter cup? In completing this structure, I've also done something else very important. I've introduced you to a double bond. A double bond is when you have 2 covalent bonds between 2 atoms. So that's one new concept I wanted to introduce. Let's see if we can really master this. Let's take a deep breath in and a deep breath out and look at some carbon dioxide. Carbon, 4 valence electrons because it's in group 4A. We have 2 oxygens. Oxygen's in group 6A. So each oxygen has 6 valence electrons for a total of 12. That gives us 16 total valence electrons to build our Lewis structure with. Well, carbon loves to be the central atom. So I draw my Lewis structure. That cost me 4 valence electrons. I have 12 left over. I want to make my outlying atom happy. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now I've completed the octet for my oxygen. I've given each oxygen now a total of 8 electrons. 2, 4, 6, 8. 2, 4, 6, 8. And one of my dots isn't very big. I'm going to make that dot. There we go. I didn't want it to have electron inferiority complex. So I needed to use 6 lone electrons to complete each of my oxygens. I have 2 oxygens, so I used 12 electrons, and that cost all of my building fund. I'm out of money. And I'm out of my money before my carbon's happy. Carbon only has 2, 4 electrons. So you say, don't worry. I see some lone pairs of electrons on oxygen. You can form a double bond, no problem. So let's form a double bond. I've formed my double bond, and let's see, everybody should be happy now. 2, 4, 6, 8. Oxygen's happy. Carbon has 2, 4, 6. Ugh. Carbon's still not happy. I still don't have any electrons. What can I do? Well, if sharing one pair was good, sharing another pair must be better. All right. I could take another pair of electrons from that oxygen, but that seems awfully unfair when this guy over here hasn't been made to share anything. So it turns out that this guy is going to be forced to share another pair. Or, I mean, this guy's going to be forced to share a pair. We'll go into the reasons for that in part 2 of our Lewis structure lecture, but right now, take my word for it, it creates a nice symmetry. It also does something else important. First, it completes our octet rule. 1, 2, 3, 4. Well, 2, 4, 6, 8. Carbon's happy. 2, 4, 6, 8. That oxygen's happy. 2, 4, 6, 8. That oxygen's happy. But in doing this structure for my carbon dioxide here, I'm doing something else. Remember, we started this lecture by saying elements in group 4A want 4 bonds. Elements in group 5A want 3 bonds. Elements in group 6A want 2 bonds. 7A 1 bond. Look at our structure now. By sharing our second pair of electrons with this oxygen atom, instead of forcing this guy to share 3, how many bonds have we given this oxygen? 2. How many does it want? It wants 2 bonds because it's in group 6A. So oxygen wants to form 2 bonds. So that's one way we know that this is going to be a good structure. We've given each oxygen's 2 bonds. Carbon's in group 4A, and we managed to give it 4 bonds. So that's another way we know that this is a very good structure. Let's take a look at another case scenario here. Let's take a look at sulfur trioxide. Sulfur is in group 6A, so it has 6 valence electrons. We have 3 oxygens. Oxygen's in group 6A, so each of them has 6 valence electrons. 6 times 3 is 18. 18 plus 6 is 24. So that's our building fund. We have 1 girl in the bar and 3 guys. So there's our skeletal structure. That cost us 6 electrons. It leaves us with 18 left over. Each oxygen right now has 2 electrons, and we'll need 6 more to complete its octet. So 2, 4, 6, 2, 4, 6, 2, 4, 6, 2, 4, 6. So that cost me 18 electrons. 6 times 3, 18. That cost me all my building funds. And sulfur is still not happy. Sulfur only has 2, 4, 6 electrons. Oh no, what are we going to do? And you're saying, not a problem, we got this. How do we got this? We got this because we know we can form a double bond, and that's exactly what we're going to do. We're going to take a pair from one of those oxygens and form a double bond. And when we do that, we get that structure. Now, is everybody happy? Let's see. 2, 4, 6, 8. So that oxygen's happy. What about my sulfur? 2, 4, 6, 8. So that sulfur's happy. And this oxygen, 2, 4, 6, 8. It's happy. Kind of. What do I mean it's happy, kind of? It's being treated unfairly! Can't you see that? There are 3 oxygen atoms out there. And what did we do? We randomly picked on one and forced it to give up its electrons. Is there any justice in that, I ask you? Is there? No, there's no justice in that. What we did was randomly bully one of those oxygens. And that's just not right. And Mother Nature doesn't think it's right either. So guess what? That's not what happens. Instead, what happens, instead of one oxygen being forced to surrender that pair of electrons to form that double bond, a pair of electrons is going to float between all of these oxygen atoms. In reality, what's going to happen is we're going to get a structure that acts as if a double bond exists between not just one oxygen and the sulfur, but exists between all the oxygens and the sulfur. So what we have is we have a situation where this double bond can be thought of as existing between all of these atoms. You'll see textbooks attempt to draw this sometimes, or attempt to illustrate this concept by drawing something that looks like, by drawing something that looks like this. To try to represent that you've got a double bond kind of floating between all of them. The situation gets even more complex because this double bond here doesn't exist between all of them, doesn't exist for a second temporarily. Instead, it's a synthesis. You know what? Let's just cut to the chase. Here's the way to think about what's going on between our oxygens and our sulfur. Has anybody here seen a tuning fork? Everybody here has seen a tuning fork. You hit a tuning fork on a desk and what happens? It vibrates. The tongs vibrate back and forth. And when you look at it, it looks like instead of there being just one tuning fork, it looks like you have lots of tuning forks. The same way we can think of what's going on with this double bond. This double bond can be thought of as resonating or vibrating between each one of these oxygens and the sulfur. Because this is a convenient way of thinking about this, we actually refer to the three structures that I've drawn here as resonance structures. None of these resonance structures actually exist. What actually exists is a combination of all three. However, we don't have a good way to draw a combination of all three. So what we do as chemists is we draw all three separately with double-headed arrows between them. And this is the concept of resonance. You can think of it as a floating double bond, you can think of it as a tuning fork. But resonance structures are used to represent that floating double bond, or that communal pair of electrons. Let's kick up the difficulty a notch and begin looking at scenarios where you have multiple central atoms. Let's add a degree of difficulty here, and let's look at some propane and propane accessories. Here we've got a larger molecule than we've ever dealt with before. We have 3 carbons and 8 hydrogens. The steps are going to be the same, but with a twist. We have 3 carbons, and carbon is in group 4A, so it has 4 valence electrons. So 3 times 4 is 12. Then we have 8 hydrogens. Hydrogens in group 1A, so each hydrogen has 1 valence electron. 8 times 1 is 8. So we have 20 total electrons to build our structure with. Next, we need to determine who the central atom is. Alright, well, carbon likes to be the central atom. But the problem becomes for us now is how do we define it as a central atom? I mean, do we do something like this? The answer turns out to be yes. We want to have one atom viewed as the central atom. In this case, I'm going to write it a little bit neater so I don't run out of room here. I'm going to attach my two of my carbons to one of the other carbons. So I've got two carbons attached. Then I want to attach my hydrogens. Now, just in theory, let's say that we attached or tried attaching all 8 of our hydrogens to our carbon. If we do that, and I'm not even sure I've got 8 there, now I've got 8. We have a problem, because how many electrons do we have around our carbon? 2, 4, 6, 8. We've got 16, we got 20 electrons around our carbon. Carbon's in the second energy level. It can only hold 8 valence electrons in its valence shell. It can't hold 20 electrons, so that can't be right. So what can we do here? Whoops, just a second here. Now things are a little bit cleaner for us. So we obviously can't place all the hydrogens around that one central carbon. So what can we do? And this is where what I was saying at the very beginning of the lecture comes into play. We said that elements in group 4A want 4 bonds, elements in group 5A want 3 bonds, 6A 2 bonds, and 7A want 1 bond, and group 8A thinks Sean Connery was the best one. You will be tested over that later. Daniel Craig and Roger Moore are also acceptable answers. George Lazenby just earned you bonus credit and a lot of sympathy from me. But at any rate, I digress. Carbon is in group 4A. That means it only wants to form 4 bonds. So we're going to try to make our structure so that each carbon's only participating in those 4 bonds. So our central carbon right now has 2 bonds. So it can form 2 more. So it's going to form bonds with 2 more hydrogens. This carbon right here is only participating in 1 bond. So it can participate in 3 more. So it can bond with 3 more hydrogens. This carbon over here has only 1 bond, so it can participate in 3 more. So it can bond with 3 more hydrogens. And what do you know? We've found a partner for all of our hydrogens because we've bonded 1, 2, 3, 4, 5, 6, 7, 8. 8 hydrogens. So we now have found a home in our skeletal structure for all of our carbons and all of our hydrogens. If we were to count up our number of electrons, we would say that we've used 1, 2, well actually I need to count by 2's, don't I? Very good, and I have the PhD here. 2, 4, 6, 8, 10, 12, and I lost count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Woohoo, I can now pass kindergarten. So I used 20 electrons to build my Lewis structure. That exhausts my building fund, so I must be done. Is everybody here happy? Well, each hydrogen has 2 electrons, so it's definitely happy because hydrogen's happy with 2. How about our carbons? 2, 4, 6, 8, so that carbon's happy. How about this carbon? 2, 4, 6, 8, so it's happy. And this carbon right here, 2, 4, 6, 8, so it's happy. Everybody's happy. Boom! All right, let me see if I can simplify this down for you again. What we've seen here is a pattern that I call a carbon chain. Whenever you have a bunch of carbons, those carbons are going to want to form a chain with each other, or form a big molecule with each other. So if you have a molecule with a lot of carbons in it, like our methane here, and I'm sorry, I don't know why I said methane, it's not methane, propane, and propane accessories. So when you have a compound in front of you with a lot of carbons, take those carbons and connect them all together in a series. That's the first thing you'd want to do. Then, complete your molecule in such a fashion that each one of those carbons has 4 bonds. So, when drawing the Lewis structure for a compound with more than one carbon, make a carbon chain, then complete the Lewis structure so that each carbon is participating in 4 bonds. So we drew our carbon chain for our methane, then we want to complete it so that each one's completing in 4 bonds. This carbon has 1 bond, 1, 2, 3, 1, 2, so that we've got 1, 2, 3, 4, 1, 2, 3, so 1, 2, 3, 4. And then everything else is going to be hydrogen at the end of one of those bonds, because that's all we've got left. So that's what you do when you're faced with multiple hydrogens. I mean multiple hydrogens faced with multiple carbons. If we wanted to, we could do another one like that. And I don't know about you, but I surely do. Alright, we've taken a look at the barbecue. Let's go camping. We've got that compound looking at us on an exam. So you're going to say, I've got a lot of carbons. So the first thing I'm going to do is I'm going to connect all those carbons. 1, 2, 3, 4. And I'm going to count my valence electrons real quickly. 4 carbons. Each carbon has 4 valence electrons because it's in group 4A. So that's a total of 16 valence electrons. I have 10 hydrogens. Hydrogens in group 1A. So each hydrogen has 1 valence electron for a total of 11. 11. I can't multiply today. 10 times 1 is 10. I promise you guys, I did go to kindergarten. I even got good grades, except I did have to stay in one time during recess because I was told I had sloppy scissor skills. But that's a story for another day. So I've drawn my carbon chain connecting my 4 carbons. Now I want to make sure that each one of these carbons has the possibility of doing 4 bonds. So I'm going to have to draw 1, 2, 3 more bonds for my terminal carbon here. Then this carbon already has 2 bonds, so it's going to want 2 more. Same for this guy. And then this guy down here only has 1 bond, so it's going to need 3 more since it wants to do 4 bonds. Now can we fill all these bonds with hydrogen? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ta-da! So that's 10 hydrogen, which is the number we have in our problem. So now we need to count and see if our valence electron total is correct. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, and yay, Dr. Kelly can count again. And there's your Lewis structure for butane. All right, let's look at another scenario here. Let's look at the compound. This is actually one of those polyatomic ions you've memorized, acetate. One of the reasons we write the chemical structure for acetate like we do is to help provide us with information on the connectivity. But before I get ahead of myself, let's total up our valence electrons. We have 2 carbons at 4 valence electrons each. We have 2 oxygens at 6 valence electrons each because oxygen's in group 6A. So that's 12 valence electrons. Then we have 3 hydrogens, each bringing 1 valence electron to the table for a total of 3. So that gives us 15 plus 8 is 23. Then we have another thing. we have a negative charge. If a species has a negative charge, does it have an extra electron, or is it short an electron? If it has a negative charge, it has an extra electron. So, because we have a -1 charge, that means we have 1 extra electron. So we actually have a total of our building fund, or total number of valence electrons, of 24. So we're going to draw our skeletal structure. Notice how our 2 carbons are separated, sign that we have a carbon-carbon chain. So we're going to make 2 central atoms carbon. Then we're going to connect things to the carbon. Remember, a carbon can only be connected to 4 things. And I see these 3 hydrogens here next to that carbon. So I'm going to place 3 hydrogens around that carbon. Then I see these 2 oxygens here next to this carbon, so I'm going to place the 2 oxygens next to that carbon. To draw that skeletal structure cost me 2, 4, 6, 8, 10, 12 electrons. So I have to subtract 12 electrons from my building fund. Now I need to make my outlying atoms happy. Well, hydrogen's happy with 2, so they're all set. Each of my oxygens, however, only has 2 currently. They want 8, so they each need 6 more. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So 6 times 2 is 12. So I had to draw 12 dots, so that cost me my last 12 valence electrons. I'm out of electrons in my building fund. How many electrons does everybody have? Each hydrogen has 2, so it's happy. All of my hydrogens are happy. This carbon has 2, 4, 6, 8, so this carbon's happy. This oxygen has 2, 4, 6, 8, so it's happy. This oxygen has 2, 4, 6, 8, so it's happy. This carbon, however, only has 2, 4, 6, so it's unhappy. It wants 8. Where am I going to get 2 more electrons to make it happy? Well, the only place that I can find extra electrons is those lone pairs on oxygen. So completely in a world of unjustness and randomness, I'm going to take 2 electrons from that oxygen and form a double bond. And that gives me now, is there any reason? All right, now let's check and see, is everybody happy? Now my carbon has 2, 4, 6, 8, so that carbon's happy. How about this oxygen? 2, 4, 6, 8. So this oxygen's happy. Everybody's happy. So I've got the complete structure with one problem still. Is there any reason I picked on this oxygen as opposed to that oxygen? No. Is that fair? No. So what must that mean? That must mean that we have resonance. So I have to draw both the possible structures, or both of the structures that the real molecule has characteristics of. Connected by double-headed arrows. But wait, there's more! That's right, this is the gift that keeps on giving. This is the gift that keeps on giving. I have an extra electron in this structure, right? Because I have acetate. Whenever you have a Lewis structure for a polyatomic ion, you place the Lewis structure in staple brackets, and then you put the charge out to the side, out to the right-hand side as a superscript. So I put my entire Lewis structure in staple brackets, and I put that charge as a superscript to the right-hand side. Let me place that in law form, just so that people are happy with it. Well, first of all, so there's the answer, right? There's the Lewis structure for the acetate ion. Just to formulate a rule real quickly, Whenever you have a Lewis structure of a polyatomic ion, place the structure in staple brackets with the charge as a superstructure to the right-hand side. As long as we're putting things in writing, let's add one more thing in writing as well. If you have an anion, add one electron. For each negative charge to your building fund. For cations, subtract one electron for each positive charge from your building fund. Let's look at a cation real quickly. First cation that pops to my mind here, the hydronium ion. If we were to tally our building fund for this, we have one oxygen with 6 electrons. We have 3 hydrogens, each bringing 1 valence electron to the table. That gives me 9 valence electrons. But then I have a positive 1 charge over here. And if I have a positive 1 charge, that means I've lost an electron somewhere along the way. So I'm going to subtract an electron from my building fund before I even begin to build. Now I draw my skeletal structure. Well, only one girl in the bar here. So now all my hydrogens crowd around. To draw that skeletal structure cost me 2, 4, 6. That leaves me 2 valence electrons left over. Hydrogen's happy with 2, so they're all happy. Place all remaining electrons on the oxygen. My oxygen's happy, so I'm done. Because my oxygen has 2, 4, 6, 8. Now, because I have a polyatomic ion, I want to place the Lewis structure in staple brackets with the charge as a superscript. Chemistry's easy, life is hard, yes? Why don't you write down Hershey's? Write down Hershey's. How can we think of chocolate without thinking of Hershey's? Everybody write down Hershey's. I hope everybody is writing down Hershey's. One last thing before wrapping up what has already been one of my longer lectures here. Let's take a look at the Lewis structure of sulfur hexafluoride. We have sulfur with 6 valence electrons. We have 6 fluorides, 6 fluorines, group 7A, each with 7 valence electrons, for a total of 42 plus 6 is 48. So we have 48 total valence electrons to build our structure with. Sulfur is going to be our central atom here, because it's the least electronegative and because it's the only girl in the bar. So how many electrons does it cost us to draw this structure? 2, 4, 6, 8, 10, 12 valence electrons. So that gives us 36 valence electrons left over. Each fluorine at the moment has 2 valence electrons and wants a total of 8. So each one needs 6 more. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6 times 6 is 36, so that uses up the rest of our building fund. So we made all our fluorines happy. How about our sulfur? Is our sulfur happy? Sure, it has 2, 4, 6, 8, 10, 12. How does sulfur have 12 valence electrons? Well, first of all, let me tell you this isn't a mistake. This compound can and does exist. How is it possible that sulfur has 12 valence electrons? Well, locate sulfur on the periodic table. Sulfur is in the 3rd period. So, the sulfur valence shell has a 3s, a 3p, and a 3d. how many electrons does sulfur have how many electrons does sulfur have in the 3D? None, right? If you wrote the electron configuration for sulfur, you'd say sulfur is neon 3s2, 3p2, right? Nothing in its 3D. That means that the sulfur atom has a completely empty d subshell. So it has room for a lot more electrons. So not only does the sulfur have room for 4 more electrons in its 3p, but it has room for 10 more electrons in its 3d. So it's entirely possible that the sulfur could have 12 valence electrons. Now let me ask you another question as long as we're on this subject. How about oxygen? Could oxygen have 12 valence electrons? No, it couldn't, right? No, why not? Oxygen is in the second period, so its valence shell is the second energy level. Its valence shell only has the 2s and the 2p, so it can only hold 8 electrons maximum. It doesn't have that empty d. To summarize, elements in the third period or higher, and by higher I mean numerically, may exceed the octet rule because they all have an empty d. Now, this is an exception. This is a rare exception. It usually occurs when the element is bonding to a very small atom that is highly electronegative. In other words, fluorine or chlorine. Just because this can occur doesn't mean it will occur. Don't try to force this into happening. Only exceed the octet rule when you're dealing with something where when you follow those rules you wind up with more around that central atom. Elements in the first and second period cannot exceed the octet rule. Elements in the second period cannot exceed the octet rule. Only elements in the third period are higher. And even then, that's an exception. That wraps it up. Good luck on the homework.